There are places on Earth where life is not supposed to thrive, places where the ground cracks open under relentless heat, where the air itself feels dry enough to erase memory, where rain is not a season, but a rumor. And yet, in one of those places, something impossible is happening. Water is flowing, not in small amounts, not as a rare miracle, but in vast, controlled, engineered volumes. Pipelines stretch across barren land. Reservoirs appear where there should be none. Green patches interrupt endless shades of dust. At first glance, it feels like a contradiction, because this isn't just any desert. This is the Negev, and the Negev doesn't forgive mistakes. To understand the scale of what's happening here, you have to start with the problem. Israel is not a large country. In fact, it ranks far down the global list in terms of land area, just around 8,100 square miles in total. That alone wouldn't be unusual. But here's the detail that changes everything. More than half of that land is desert. Not semi-arid land, not fertile plains waiting for rain. Actual desert. The Negev alone stretches across roughly 5,000 square miles, a massive expanse of sand, rock, and silence. So the question was never whether to use the land. The question was, how do you survive when most of your country isn't meant to support you? Because the Negev isn't just dry, it's extreme. Average daytime temperatures fluctuate between 77 and 88 degrees Fahrenheit depending on location. At night, they drop to somewhere between 57 and 66 degrees. Manageable at first glance, but that's misleading because during peak summer, the heat spikes violently. Temperatures can reach nearly 122 degrees Fahrenheit, and when they do, the desert transforms. It becomes something else entirely, a place where standing still feels dangerous, where the horizon shimmers, not with beauty, but with distortion. And then there's the rain, or rather, the lack of it. In the southern Negev, precipitation is almost non-existent. Summer brings nothing, not a drop. The rest of the year isn't much better. Total rainfall barely reaches 2 inches annually. In some areas, it's closer to 0.9 inches. To put that into perspective, even parts of the Sahara Desert receive more rain. The northern Negev fares slightly better, with occasional rainfall between 1.6 and 2 inches during certain periods, and an annual average exceeding 8 inches. But even that is still incredibly dry. So what you're looking at is not just a challenging environment, it's a hostile one. And yet, people live here, not just small communities or isolated settlements, cities, large ones. Beersheba, for example, is home to over 200,000 people. Think about that for a second. Hundreds of thousands of people living in a place where water shouldn't even be available. Which leads to a deeper question. Where is the water coming from? At first, the answer seems straightforward. It's transported, engineered, forced into existence. Back in the mid-20th century, a vision began to take shape, a bold one. If water couldn't exist naturally in the south, then it would be moved there, from the north, from one of the most critical freshwater sources in the region, the Sea of Galilee. What followed was one of the most ambitious infrastructure projects of its time, a national water carrier system, completed in 1964, spanning roughly 80 miles. But distance alone doesn't tell the story, because this wasn't just a pipeline. It was a network, massive pipes, open canals, underground tunnels, storage reservoirs, and powerful pumping stations. Together, they formed a system capable of moving approximately 19 million gallons of water every single hour. That's about 449 million gallons per day. Let that sink in. Nearly 500 million gallons every day flowing across a country into a desert. At first, it worked. More than that, it changed everything. Water reached places it had never reached before. Secondary pipelines branched off from the main system, pushing deeper into the Negev. Settlements expanded, cities grew. Agriculture began to appear where it had no business existing. For a moment, it felt like the problem had been solved. But systems like this have a hidden weakness. They depend on something. And in this case, that something was finite. The Sea of Galilee wasn't endless. Over time, droughts began to affect water levels. Monitoring systems detected the drop, and the implications were clear. If the source fails, everything fails. That's when the strategy shifted, not slightly, radically. Instead of relying only on fresh water, Israel turned towards something much larger, much more abundant, and until then, mostly unusable: the Mediterranean Sea. At first, it sounds obvious: an entire sea of water right next to the country. Why not use it? But there's a problem: salt. Seawater can't be used for drinking. It can't be used for agriculture, not without transformation. And that transformation requires technology. So they built it, not just one plant, but many. Desalination facilities capable of converting salt water into fresh water at an industrial scale. Their combined output between 23 and 39 billion gallons per year. One of the most advanced among them, Sarek, pushes those limits even further. And these plants aren't isolated. They're connected directly to the national water system, integrated, seamless. Here's where things get interesting. Because desalinated water isn't used directly, some of it is redirected back into natural reservoirs, even the Sea of Galilee itself. Think about that. Water from the sea, cleaned, pumped inland, then used to refill a freshwater lake. It's not just distribution anymore, it's control. And the system doesn't stop there, because there's another layer, one that operates quietly, mostly unseen, underground. Beneath the surface lies the mountain aquifer, a vast body of groundwater, ancient, hidden, valuable. On paper, it offers a safe yield of about 95 billion gallons per year. That's the amount that can be extracted without causing long-term damage. But reality doesn't always follow theory. By 2023, extraction had reached around 158 billion gallons annually, far beyond the safe limit. And that's where the risk begins. Because aquifers don't refill quickly, not in climates like this. And worse, beneath the freshwater layer, there's salt water. If too much fresh water is removed, the balance shifts. Salt water rises. Contamination begins. And once that happens, reversing it becomes nearly impossible. So now the system faces a paradox. The more water you need, the more careful you have to be. Which leads to the next evolution: not sourcing water, not transporting it, but reusing it. And here's where the story takes a turn most people don't expect. Water that has already been used doesn't disappear. It comes back. Water, once used, is supposed to be gone. That's the assumption most systems are built on. You consume it, you dispose of it, and you move on. But here, that rule doesn't apply. Because in this system, water doesn't end. It loops. Somewhere beneath cities, behind infrastructure no one really sees, a second network exists. Not for clean water, but for what comes after: wastewater. At first, it sounds unremarkable. Every country has sewage systems. Every city processes wastewater in some way. But what happens next is where things start to diverge. Since the early 2000s, massive investments have been poured into something most people don't think about: recycling water. Not on a small scale, not as an experiment, but as a core strategy. Dozens of treatment plants were built, 67 to be exact, and among them, a smaller group, just 10 facilities, handle more than half of the total recycled water. But the real number, the one that changes everything, is this. About 87% of all wastewater is reused. Let that settle in. Almost every drop that goes down a drain finds its way back into the system, cleaned, processed, repurposed. Compare that to other countries where reuse rates often struggle to reach even 10%. Suddenly, this isn't just efficiency, it's dependency. One of the most critical pieces of this system operates near a major urban center, a reclamation facility processing around 97 million gallons of wastewater every single day, day after day. No pause, no margin for failure. But here's the part that makes it truly unusual. This water doesn't stay where it's treated. It moves. Pipelines carry it south, into the Negev, into the desert. And there, it does something unexpected. It feeds life. Up to 60% of the greenery in parts of the Negev depends on this recycled water. Not fresh water, not rainfall, but water that has already been used once before. And suddenly, the idea of waste starts to disappear, because nothing is wasted anymore. Everything is part of a cycle. But even that isn't the strangest transformation happening in the desert, not even close. Because at some point, the goal shifted. It was no longer just about survival, or efficiency, or even sustainability. It became something else, something more ambitious. The idea of creating a forest in a desert. At first, it sounds like a contradiction. A forest requires water, shade, stable soil, and consistent climate conditions. The Negev offers almost none of that. And yet, it exists. The Yatir Forest, located in the northern edge of the Negev, spanning around 11 square miles, it stands as one of the largest man-made forests in the region. But what truly sets it apart is not its size, it's the fact that it shouldn't be there. Millions of trees were planted, roughly 4 million, most of them Aleppo pines, species chosen not for beauty, but for survival. Because this wasn't about aesthetics, not really. The forest had a purpose, several in fact. First, to stop the desert itself. Deserts don't stay still, they expand, slowly, quietly, but relentlessly. Sand shifts, vegetation disappears, boundaries move, but a forest changes that. Roots stabilize the soil, canopies reduce wind speed, moisture is retained. Over time, something subtle happens. The desert's advance slows, and in some areas, it stops. Second, carbon. The trees act as a massive carbon sink, absorbing CO2 from the atmosphere, locking it away. And here's where it becomes even more surprising. Research has shown that this forest absorbs carbon at levels comparable to forests in much wetter regions. A forest in a desert, performing like one in a temperate climate. But that's not all. The forest also changes how water behaves. In a place where rain is rare, every drop matters. Without cover, evaporation quickly occurs under intense sunlight. But with trees, shade reduces evaporation. Moisture lingers. Even the smallest rainfall events become more effective. And because of all this, the forest has become something else entirely, a laboratory. It's part of a global research network, a system of monitoring towers measuring the exchange of carbon dioxide, water vapor, and energy between land and atmosphere. Data flows out of the desert into global climate models. Nearby, research institutes experiment with crops, dates, grapes, plants that can survive in dry, saline conditions. The goal? To push agriculture further into places it was never meant to go. But every system has a cost, and this one is no exception. Because not everything thrives in a forest, especially in a place that was never meant to have one. Some native species struggle. They evolved for open landscapes, for wide visibility, for heat and exposure. Now their environment has changed. Predators behave differently, food chains shift, balance is disrupted. And then there's the forest itself. Not all trees survive. Between 5 and 10% have died over time. Droughts hit harder than expected. Recovery is slow. Add to that grazing animals, sheep, goats. They feed on young saplings before they can grow. And beneath it all, the soil. Dry land soil is fragile. It has a crust. Break it, and the ecosystem beneath it suffers. Small organisms, lichens, fungi, microorganisms disappear, and with them, entire micro-food chains. So while the forest grows, something else fades, and that raises a question, a quiet one, but an important one. Is this restoration or replacement? Because sometimes creating something new means losing something old. And yet, despite all of this, the system keeps expanding, because beyond the forest, beyond the pipelines, beyond even the recycled water, there is another layer, one that turns the impossible into something almost routine, agriculture, but not the kind you expect. At a distance, it looks convincing. Green fields stretching across dry land, orderly rows of crops, life where there should be none. If you didn't know better, you might think this was always possible, but it wasn't. And maybe it still isn't. Because what you're seeing isn't nature adapting. It's something else. Something engineered, controlled, calculated down to the last drop. Agriculture in a desert isn't supposed to work. Not at this scale. Not with this level of productivity. And yet, it does. Crops grow here that shouldn't survive. Wheat, sunflowers, melons, chickpeas, pomegranates, almonds, olives, even cotton. Cotton, one of the most water-intensive crops on Earth, growing in a place where rain barely exists. So what's the trick? Because this isn't luck, and it's definitely not natural rainfall. The answer lies in precision. Traditional irrigation is simple. You flood the field, water spreads, some of it reaches the roots, a lot of it doesn't. It evaporates, it runs off, it disappears. In a place like the Negev, that approach would fail almost instantly. The water loss would be catastrophic. So instead, they changed the rules. Water is no longer spread, it's delivered, directly. Drip irrigation. At first, it sounds almost too simple. Small emitters release tiny amounts of water right at the base of each plant, drop by drop, controlled, measured. But the impact is massive. Water use drops significantly. Evaporation is minimized. Weeds struggle to grow. Soil erosion decreases. Every plant gets exactly what it needs, no more, no less. And suddenly, the desert becomes manageable. But here's where things get interesting. Because once you control water that precisely, you don't just grow crops, you optimize them. Yields skyrocket. Tomatoes, for example, reach around 300 tons per 2.4 acres. The global average? About 50 tons. That's not an improvement, that's a leap. Citrus production follows the same pattern. High output, high efficiency. Even dairy production, something not directly tied to desert farming, reaches levels far beyond many other regions. So now the question changes. It's no longer, how do you grow food in a desert? It becomes, how are you outperforming the rest of the world from a desert? And the answer isn't just water. It's systems. Everything is connected. Water supply, recycling, irrigation, crop selection. Nothing is left to chance. But even this isn't the most unexpected part, because at some point, someone asked a different kind of question. If you can grow crops in the desert, what else can you grow? The answer? Something that makes even less sense. Fish. Yes, fish. Not near the coast, not in rivers, but in the middle of the desert. At first, it sounds impossible. Fish need water, clean water, stable conditions. But beneath the surface of the Negev, something unusual exists. At depths between 50 and 100 feet, there are pockets of water, warm, around 98 to 104 degrees Fahrenheit, and surprisingly, low in salinity. Ancient water, left behind from a time when the region wasn't as dry, when rain fell more frequently, when the desert wasn't quite a desert. This water was trapped underground, heated over time, preserved, and now it's being used. Fish farms tap into these underground sources, pump the water up, create controlled environments. Species like tilapia, bream, catfish, even barramundi, all raised in the desert. But again, the system doesn't stop at production, because once the fish are grown, the water doesn't get discarded. It changes role. Fish release waste, metabolites, nutrients, and instead of treating that as a problem, it becomes an advantage. The water becomes nutrient-rich, perfect for agriculture, so it's redirected, used to irrigate crops. Plants absorb the nutrients, clean the water in the process, and the cycle continues. A closed-loop system. Water feeds fish, fish enrich water. Water feeds plants, plants clean water. Nothing wasted, everything reused. It sounds efficient, and it is. But it also raises a subtle question. When a system becomes this controlled, this optimized, this dependent on constant input, how fragile is it? Because unlike natural ecosystems, this one doesn't run on its own. It needs energy, constantly. And that brings us to the next layer, the one that powers everything. Because moving water, cleaning it, recycling it, pumping it from underground, none of that happens for free. It requires something else. Something the desert has in abundance, and something that, until recently, was barely used to its full potential. The sun.
Everything you've seen so far, every drop of water, every green field, every tree, none of it exists on its own. Because this system, no matter how advanced, has one critical dependency: energy. Without it, the water stops moving. The desalination plants shut down. The recycling systems go silent. The desert returns to what it was. So the real question becomes, where does all that energy come from? At first, the answer might seem obvious: conventional power, fossil fuels, imported energy. But that would create a new problem: dependence. And in a system built around control, dependence is a weakness. So instead, they turned to something already there, something overwhelming, something unavoidable: the sun. The Negev isn't just dry, it's exposed. Vast open land, minimal cloud cover, relentless sunlight. Conditions that are harsh for humans, but perfect for energy. And so the desert began to change again. Not with water this time, but with mirrors. Large-scale solar installations started appearing across the landscape, at first scattered, then expanding. One of the most striking examples lies not far from Beersheba, a massive solar complex. But it's not just one plant. It's a combination of technologies, each designed to capture the same thing in a different way. The first system looks almost mechanical in its elegance. Rows of curved mirrors, parabolic troughs, stretch across the land. They track the sun, slowly, precisely. Their purpose? To focus sunlight onto a pipe running through their center. Inside that pipe, a heat transfer fluid. As sunlight concentrates, temperatures rise, energy builds. And that energy doesn't disappear when the sun sets. It can be stored for hours, up to 4.5 hours after sunset, which means the system doesn't just generate power, it extends it. But that's only the first layer. The second is more dramatic. Thousands of mirrors, individually controlled. They move constantly, adjusting, and tracking the sun's exact position in the sky. Each one reflects light toward a single point, a tower, a massive central tower rising into the desert sky. At one point, it stood around 853 feet tall, one of the tallest of its kind in the world. At the top, a receiver. And when all those mirrors align, they create something extraordinary, a concentrated beam of solar energy, intense, focused, almost unnatural. The heat generated there is extreme, enough to produce steam, enough to drive turbines, enough to generate electricity on a massive scale. This single system produces around 320 gigawatt-hours of energy per year. To put that into perspective, that's enough to power around 120,000 homes. But again, it's not just about homes. This energy feeds the system: water pumping stations, desalination facilities, irrigation networks, all of it connected. And then there's the third layer, less dramatic, more familiar. Photovoltaic panels, flat arrays that convert sunlight directly into electricity. No moving parts, no towers, but still essential.
Together, these three systems create something powerful: redundancy, flexibility, scale, energy from the same source, captured in different ways. And now, the desert isn't just being transformed by water, it's being powered by light. But here's where things take a step back, because once again, there's a deeper question. If all of this depends on constant energy, constant maintenance, constant control, what happens if something breaks? What happens if the system stops? Because unlike natural ecosystems, this one doesn't recover on its own. It doesn't self-balance. It doesn't regenerate without input. It requires precision, and precision is fragile. Still, the system works, not just in theory, but in practice. The Negev today contributes around 40% of the country's agriculture. Think about that. A desert producing nearly half of a nation's agricultural output. Crops grow, fish farms operate, forests stand, cities expand, all supported by a network that shouldn't exist, and yet it does. Which brings us back to the beginning, water in the desert. At first, it looked like a contradiction, then an engineering solution, a system. But now, it looks like something else entirely, an experiment, one that's still running, one that hasn't fully revealed its outcome. Because the real question was never, can you make the desert green? The real question is, at what cost and for how long? Groundwater is still being pushed beyond safe limits. Desalination requires constant energy. Ecosystems are being reshaped, and climate itself is changing, So this system, no matter how advanced, exists in a delicate balance, a balance between control and consequence, between innovation and risk. And maybe that's what makes it so compelling, because this isn't just a story about water or agriculture or energy. It's a story about limits. How far can human ingenuity go before it runs into something it can't control? And in a place like the Negev, that question doesn't feel theoretical, it feels immediate. Because beneath the green fields, behind the flowing water, under the hum of solar towers, the desert is still there, waiting. Amazing discoveries. Make sure to subscribe and hit the bell icon. Share this video with friends and join the discussion on what these findings could mean. Your thoughts and questions are important, so let's explore incredible mysteries together.